Hello, grade 10. Here is our very last screencast lesson of the year. We have made it through, or almost made it through virtual school, guys. I'm impressed. I know it's been hard for all of us at different points, some harder than for others, but stay strong. Last lesson, an assignment, unit test, exam, but the end is in sight. So we're doing lesson number 7, factors affecting reaction rate. Here is the template for today, so you need to have space to do reaction rate collision theory, spot, activation energy, concentration, temperature, surface area, and nature of reactants, and then catalysts. There is a drawing for this one here, but I think it'll take up more space than you have on this page, so I recommend using another page for that drawing. Unless, of course, you're doing digital notes, and then you can just try and find the same picture online, or take a screencast of my video, which I know a lot of you guys do. Take a screenshot. Okay, so we have now done to our last big idea, which of course makes this our last big idea, which is how can mathematical representations be used to understand chemical reactions? So you should be going back to all the graphs we've looked at, the calculations we've done throughout the entire year. Remember, this is what your final exam is based on, is the big ideas from all the units the whole year. So you need to be able to talk about these and have really thorough notes on these to be successful on the final exam. Okay, let's start talking about reaction rate and collision theory. So we talked about collision theory already. You've seen this image before. What do you remember about it? Take a minute and think about this. What do you remember? Well, hopefully remember that collision theory is talking about the fact that for reactions to happen, the reactants have to collide. And they have to collide with sufficient energy to break the bonds in the reactant compounds to form new bonds in the products. Has to collide in the right direction so that the right atoms of each compound are colliding and then reacting with each other. So we're going to talk about reaction rate in this lesson. So in this second image here, we're listing different factors. Can you connect any of those factors to collision theory? Well, if I have a higher concentration of reactants, I'm probably going to have more likelihood of having a collision. If I have increased pressure, it only works for gases. There's going to be less space between the particles of the gas, so increased chance of a collision. Particle size, if particle size is smaller, then I have more chance of collision, or it's on a surface area. A catalyst can affect energy. Because how much energy it takes to make a reaction happen. The temperature increases the energy of the particles and can therefore increase the reaction rate, and light can also increase the energy of the particles, and some reactions require light, such as photosynthesis. So, which factors affect the energy of the collision, and then which ones affect the frequency? So we're going to look at the entire lesson is which ones are affecting energy, which are affecting frequency. Okay, so it's our every time we talk about a different factor, think about is it energy or frequency, or sometimes both. Would those factors have a bigger impact on the initial reaction rate or the mean reaction rate? Well, we know that reaction rate is always fast at the beginning. We have the largest amount of reactants available. They haven't all reacted to products yet, so it's going to, of course, have a bigger impact when we have more reactants available. But it will still have an impact across the entire reaction, but we'll see it more dramatically at the beginning. Okay, so most chemical reactions don't happen spontaneously. Materials that are left of the air will not react, but they require some sort of initial energy source to kind of get them going. And that initial energy source causes an increased rate of collisions, and that will then cause a chemical reaction. So for example, here we have magnesium ribbon, so metal here, and it's in almost every science lab, especially high school science lab, and middle school as well, around the world. It's completely stable. You leave it in your cabinet, maybe in a plastic baggie, but that's it. Nothing happens to it. But this chemical reaction is what happens. Magnesium will react with oxygen to make magnesium oxide. And if you expose it to air, it will very slowly start to have this reaction happening. And sometimes before you burn ribbon, you have to kind of clean it off if it's been oxidized. But we can do something to really increase the rate of this reaction. Okay, if you add thermal energy, that's going to immediately cause a very quick reaction, really bright effects, let's say. So here's a little video of this happening. So this person's going to hold a piece of magnesium ribbon, and they're going to hold it in the crucible tongs into the Bunsen burner flame. And of course, if you were in class, I do this for you guys in the lab. Don't look directly at the light. They're talking about what they're doing, they're going to react it, blah, blah, blah. We're going to increase the energy of the particles, adding thermal energy. Come on, just do it. And to produce magnesium oxide, MgO is magnesium oxide, an ionic compound. Come on. There we go, finally. Whoa! Magnesium is often used in fireworks. Can you guess why? If you look what's left here, it's very powdery, and when we drop it, it kind of breaks because it's magnesium oxide powder. So this is a chemical reaction. What are the signs of a chemical reaction that we saw? Do you remember the 5 signs of a chemical change? Well, heat or light produces when there's definitely light produced, and it's hard to reverse. You can't take that white powder and turn it back into magnesium ribbon. Can you balance this equation? It's a synthesis reaction of magnesium and oxygen to make magnesium oxide. Can you balance it? Don't forget, you have to balance equations. There we go. 2 magnesiums plus 1 oxygen gives 2 magnesium oxides. Okay, so I want you to draw the top graph here, or find the top graph. This one you already have in your notes from earlier. So remember, to begin a chemical reaction, we have to have enough kinetic energy in the reactants to break those bonds in their reactant compounds. And the minimum energy in these collisions to cause this reaction to break those bonds, that's called the activation energy. The symbol for it is capital E for energy, little a, subscript A for activation. And on a lot of graphs, you see it as this kind of bump, often we think of it as a hill in an enthalpy graph. So this is where enthalpy is our energy of reaction, the heat energy, and this is the activation energy. The starting energy of the reactants, the ending energy of the products. Starting energy of the reactants, ending energy of the products. One of these reactions is endothermic, one is exothermic. Can you identify it? Can you remember? Okay, so for the collision to occur, the reactants have to collide with enough energy to get over this hill. Okay, and this hill is the energy it takes to get it started. Once some reactants get over that bump, that hill of activation energy, then the rest of the reactants will just continue to react spontaneously. And at this point here, the top of the hill, what's going to happen is the reactants will form what's called the activated complex. This is a transitional kind of form of the compound. It's not really reactant, it's not really product, it's in between, it's temporary. If there's enough energy available, it will continue to form product. If there's not, it will go back to reactant. So it depends on the energy whether that activated complex can then form product. So here we have carbon dioxide and nitrogen monoxide reacting. A bit of activated complexes all kind of combine together, and we're ending with carbon monoxide and nitrogen dioxide. So they're low energy reactants, high energy products. Energy is absorbed, which means this is an endothermic reaction. And here we had higher energy and we lost energy to negative delta H. It's an exothermic reaction. So remember that the difference between energy and enthalpy, we use the word enthalpy at this level. Okay? So don't draw this. We've seen these images a bunch of times. This is because it's really important. All of this fits back together again. So reaction rate fits in with activation energy here. So I have my exothermic reaction, higher reactant energy and lower product energy. Delta H is negative, and I'm losing my heat to the environment. Here's my hill, my activation energy. Here's my activation energy here. Okay, and I have my reactants are lower energy, products are higher energy, but I still have acquisition energy regardless. My delta H is positive, right? It's been an increase in enthalpy. Okay, let's talk about the factors, specific factors that affect reaction rate. We're not going to go through all of them, just 5 of them. Okay, we're going to start with concentration and temperature. So draw this one because it talks about concentration, temperature, and surface area or size of the pieces. So almost all chemical reactions are going to increase in rate when you increase the concentration of the reactants. We're not going to talk about the exceptions to this at the 10th grade level. If you take DP Chem, you will talk about it then, most likely. Okay, so do you think concentration, is that going to affect the energy of the collisions or the frequency of the collisions? It's definitely the frequency. If I have more reactants, there's a higher chance they're going to bump into each other and have a collision and then produce a product. But what temperature? If I increase temperature, does that increase the frequency or the energy? Well, if I increase temperature, that's going to actually increase both. I have a higher energy and a higher, so higher energy means I'm going to have more energy, of course, to those reactant molecules, and then higher energy, different particle theory, means more movement of particles. So they're also going to be colliding more often because they're moving more. So temperature is an effective reaction rate factor. So remember, temperature is a measure of the average kinetic energy of particles. So as temperature increases, particles are going to move faster and they're going to have more energy. Look at this image here. We have the higher the temperature and the higher concentration, the faster the reaction time. If I have lower temperature, lower concentration, less reaction time. So here's another little video of concentration and affecting reaction rate. Again, we would do this in class. So we have a test tube rack. I'm gonna fast forward this. And we have 2 reactants. We have dilute hydrochloric acid 10 mils. So 10 mils is a constant volume. Going into one test tube, they're calling them boiling tubes. And then we have concentrated HCl in the second one, also 10 mils, so the same volume. And then to each of them, we're going to add magnesium ribbon again. So magnesium, look at the difference in the reaction here. Which reaction is happening faster? Remember, this is dilute HCl, this is concentrated HCl. And how can I tell? How could you measure the reaction rate here? What kind of setup could you use if you're actually measuring this? So gas bubbles are the hydrogen gas being formed. And of course, we could measure the volume of gas or the mass change. And this in general, you can just also tell when it stops reacting, which one is done. Because if you have the same amount of magnesium going in and same amount of HCl, that's another good way to measure. To know which one is faster, well, of course, we wouldn't do that in high school. That's not detailed enough, not specific enough, precise enough. Okay, so increasing concentration increases the reaction rate almost all the time. Okay, what about surface area? So what is surface area? Is that going to affect the energy of the collisions or the number of collisions? Well, this is really important in a reaction that has 2 phases. So we have a liquid and a solid reacting together. So the reaction can only happen when my reactants collide, right? So when my solid and my liquid collide, then a chemical reaction can happen. And so therefore, the surface area of the solid will directly affect how often those collisions can happen. The smaller the pieces, or the larger the surface area, the faster it's going to have. So look at my graph here. Small pieces, faster reaction, large pieces lower, because larger pieces have a lower surface area. Okay, look at that. It's a little video here for that I want to show you before I talk about the next part. So here we have the same reactants being mixed. We have powdered calcium carbonate and a lump of calcium carbonate, and they're both reacting with HCl. Notice the rate of reaction here. Which one is going faster? There's nothing different here except surface area. Everything else is constant. Same amount of each one, because surface area, Bigger surface area means more collisions, and more collisions means more reaction. The other thing to think about for reaction rate is what's called the nature of the reactants. So every chemical reaction has kind of a basic level, how much it would normally take if you have like a regular temperature, medium kind of concentration surface area, concentration, all the kind of stuff, and that's based on the nature of the reactants, just like how reactive they are, what kinds of bonds will form. So some bonds are broken quite more quickly than others, that kind of thing. So if we look at these images here, it gives you some ideas. So if we look here at this reactivity of metals, the more reactive a metal is, the quicker the reaction rate is going to be already, just because those particular elements are more reactive. They're already going to have a quicker reaction rate. Imagine a particular table, metal reactivity increases towards the left and down, so francium is the most reactive, and non-metals increase the opposite way, so fluorine is the most reactive, of course ignoring our noble gases, which don't react at all. The kind of bond makes a difference here. So if I have a ionic bond that's the biggest, strongest bond, it takes more energy to break that bond than a covalent bond or a metallic bond. Hydrogen bonds are very weak. So how is this connected to bond enthalpy? Well, the more energy there is in a bond, the harder it's going to be to break it. So the slower the reaction rate is going to be based on the nature of those particular reactants. So we can, of course, increase reaction rate with temperature, concentration, surface area. The other thing we can talk about here are catalysts. So I want you to draw this image. The next slide has it much bigger if you want to see it to write down the text. I think it's a very useful image for this process. So catalysts, those are substances that increase reaction rate without being consumed in the reaction themselves. So because of that, we write them over the arrow. So here's manganese oxide and here's catalase. Both are catalysts for this same reaction, hydrogen peroxide becoming water and oxygen. Okay? So write it over the arrow because it's not being used up. It's not actually a reactant. And they do this by lowering the activation energy. So they don't lower the energy in the same reaction. They actually create an alternate path for the reaction to happen that makes it require less energy. Okay? So it can happen faster with the presence of a catalyst. So does this affect the energy or the number of collisions? Well, definitely the energy. It's not that the collisions don't have more energy, just the collisions require less energy to be successful in breaking those bonds. And then in biology, we often talk about enzymes. What's the difference between an enzyme and a catalyst? Well, a catalyst is inorganic and is basically an enzyme is a catalyst, but in biology, it's a protein that works in a living organism, whereas other compounds can act as catalysts and not get used up. Often metals can be good catalysts. Like here we have manganese oxide. Catalase here, ASE, is my hint. This is an enzyme. Okay? That is a great example of a connection between multiple units here. So between our digestive system stuff in our homeostasis unit and catalysts and energy reactions, it's a good connection, kind of thing that might show up on your final exam. Hint, hint, nudge, nudge. So here's that big diagram again. I really like this one because it explains really clearly the different factors that come into play here, including delta H. So I recommend you either draw this, take a screenshot, or Google it. Okay, the last thing I want to show you is your assignment. This is the second time for this unit, and you have the option to do this one instead of the Hindenburg one. We could do them both, but for me to grade this one. And what you're looking at here is you have the reaction rate for a volcano, where you have baking soda plus vinegar, and an elementary school student is going to make the biggest eruption, and they want your chemistry expert knowledge to help them. So here's a bunch of data on things affecting reaction at different factors they've tried out, and you're going to answer these 5 questions about it. You have to draw models, just like in the Hindenburg one, so you need to make sure that you draw them by hand. Someone in the Hindenburg one just Googled a diagram and used that. That's not acceptable. You have to draw your own thing. Upload a picture of it, do it yourself. Okay? So your homework for this is to upload a copy of your notes, of course, complete the assignment as well, and all 4 big ideas should also be uploaded. And make a note for me in the comments on this upload if you want me to grade the Hindenburg assignment or the volcanic eruption assignment for your summative grade for this unit. All right, guys, our last lesson. Hope it was helpful for you, and take care.